when we deal with statistics, the first thing you do is collect data. Sometimes the data is given to you, like I give it to you here. Sometimes you collect it and then deal with it, or analyzing it. So I gave you 10 consecutive days, the temperature over 10 consecutive days. Let's say they're in Fahrenheit. Okay. Hopefully you can kind of guess kind of what time of year this is, like winter. Just kidding, it's not winter. This is more like a spring, maybe a winter for some cities. Like Phoenix, just kidding, that'd be colder than that, warmer than that, stupid. Anyway, but we could tell maybe spring time. Summer where we live, it's hundreds. Anyways, so there's some temperatures over 10 days. Now the next thing you do when you deal with stats, the next thing you do is order them from lowest to highest. So we're going to take this random set of data and put them in order from lowest to highest. Now I'm going to write that down. The first, just so I remember, I want to put my data from lowest to highest. You might want to write that just to remind yourself. And then we're going to write it in lowest to highest. So go ahead and write lowest to highest and then put them in order from lowest to highest. Voila, that was pretty fast. Got my data in order from lowest to highest. You should see 10 values to make sure you got them all. Now we're going to go to something called central tendencies, which deal with mean, median, mode. Now your mean, a lot of people know that, is your average. So let's write that just to remind ourselves. We're looking for our average value. What is a median? Median is your middle value. Now, what I always thought of that, median sounds like medium, like small, medium, large, which is in the middle. Whatever works for you. Your median is the middle value. Anybody remember what mode is? The one that comes up the most. So those are key words that we're going to be looking for and using to do this. So to find the average, let's go to average. A lot of people are good at average because like GPA is a grade point average. Do you guys understand average is sum up the data and divide by how many pieces of data you have? So let's kind of write that quickly. You're going to sum data. That does not look like the word sum. So you sum the data and divide by the number of data. So how many pieces of data you have. I kind of try to make that small so you can't read it very good. But you're basically, again, taking the sum of all the data divided by the number of data. So we have to add all this up and divide by what? 10, because there's 10 pieces of data. So let me add that up for you so you don't have to do it yourself. It is going to be, when you do it, you get 827 divided by 10, which that actually is kind of nice. Just move the decimal over. So 82, that's a nice 8.7 degrees. Let's put degrees on it to remind ourselves. So your average temperature for this 10 days is 82.7, which does that look about reasonable? Yeah. Maybe. But your average temperature, which is kind of nice, that's kind of normal. People say, what's your average temperature? That's it. Next question is the middle. The median, which is the middle value. Can you look at the data and find the middle? Can you tell, you go over, wait, is there a middle value? No. So how do you find it if there is no middle? You have to average those to find what would be between. Now, could someone look between 80 and 88? Can you tell it's 84? Now, if it's harder, what you technically do is you take the two terms and you average them. So take those two middle terms, where the line is, and you divide by 2, and when you do that, you would get 84 degrees. So that's the technical way. If you can't just see it, you take the average. And the last one is the most often. And if you look at it carefully, the 90 comes up most often. So we have the most 90-degree days. The middle day of all of it is 84, but the average is 82.7. When we look at quartiles, quartiles are saying break this data into 4 parts. Right now we have 2 parts, the left and right of the median. We want to break this up, and we want to break up this. So we have 4 quarters of values. So to break this side up, wouldn't it be right here? Isn't that the middle of it? To break this side, isn't this the middle of it? So I'm going to put a line like this and this. This is not mathematical. It's just me kind of showing. Can you see now data into 4 parts? These are called your quartiles. There are 3 quartiles. They call this one Q1, Q2, and Q3. They're the numbers that break it up into 4 parts. It's kind of weird. If you have something broken into 4 parts, doesn't it take 3 pieces to do that? They're the 3 numbers that break it up into 4 parts, quarters. So let's write that, what that means exactly. Quartiles. The quartiles are values in the data that separate it into 4 equal parts. So the values that separate it into 4 equal parts. So, and we have a Q1. Oops, there's a 1. We have a Q2 and a Q3. Q stands for quartile. So if we look at the graph, that's Q1. The median is always Q2, and Q3 is right there. So Q2 is easy. Q2 is always the median. You might want to write median underneath that. It's always the median. Q1 is that 72 degrees. And Q3 is 90 degrees. So again, Q1 is the average of the left side, and Q2 is the average of the right side. So next, I want to do a box and whisker plot. So we're going to put this data and make a picture of this data on a number line. So the first step is to make a number line, and I want to put the median in the middle. Now if we look at the data, if we start at 84 in the middle, all right, and I go, the highest number from 84 is 95, and the other one's 70, I'm going to go by 4s, not 5s. There's a reason for it. So I'm going to go by 4s. So I'm going to call this 88. And then go by 4 again. Wouldn't that be 92? And do I have to go farther to fit the 95? Yeah, let's go one more, which would be 96. Then I can fit up to 95 on it. And then I go down by 4s. So I'm going to go, that'd be 80. And then that would be 76. Will that fit all my data? No, I got all the way to 70, so let's keep going. So that's 72. I still didn't fit it all. So let's go all the way to 68. And I'm making a number line, and we're going to put, we're not going to write the data, you'll see what I'm going to do here. But what I'm going to do is I am going to put all the quartiles and make a box by the quartiles. So my lower quartile is 72. So I'm going to make the edge of the box here is 72. My median was at 84. And my Q3, which is my upper quartile, is 90, which is right about there. Got that? And then I'll make a box. That right there is my box of my box and whisker. All I do again is use my quartiles to make a nice little picture of a box. Now, what is a whisker? Whiskers are, well, what is my biggest value and my smallest value? My biggest value is 95. So I go over here and approximate 95. Put a line, and I just put a whisker. So kind of one-sided whisker. And what's my smallest value? 70. Put a line at 70 and put a whisker. So now what I have is a box with whiskers. The box represents my quartiles, my Q1, Q2, Q3, which we might want to write that. So remember that's Q1, Q2, Q3. You might want to write those on there. And these are the edges. It's a picture of your data. And we'll get used to how that helps, but it's like a graph of your data. Now, percentiles are basically what percent of the data is below a given number. percentiles, let's just write that out. Percentile is the percent of the data below or less than, let's put less than, it's actually below, less than a given value or data point. So what I mean by that is, well, what percent of the data is below a given value? So let's say 96. What percent of your data is below 96? 100%. Okay, what percent of your data is below 40 degrees? 0%. Okay, what percent of your data is below 94 degrees? 50%. Oh, but, sorry, what did I say? Okay, sorry. Okay, I said 94. So 84. What percent of your data is below 84? 50%. Sorry, I said the wrong number. Percentile tells us what percent of the data is below or less than a given blank. So again, if I said what percent of the data is below 72, well, that's 1 out of 10, 10%. So it's kind of weird to get used to. Percentile is what percent is below. Now, but if I say something like, what is the 30th percentile? If I ask the question, what is the 30th percentile? It's a different way of saying it. I didn't say what percent is below. I said, what is the 30th percentile? So what value has 30% of the information below it? What value would have 30% of the information below it? So what we have to do is, well, what is 30% of 10? Because don't we have 10 values? Are we okay? So how do we find 30% of 10? Isn't 30% 0.3 of the 10 values? So what is 10 times 30%? So what that means, 3 values. So 3 values are 30% of the data. Are you okay with that? 30% of the data is 3 values. So what 3 values, so what's the edge that would be above that? So what I want to say here basically is, what would be my 30th percentile? It's actually going to be 80. That's kind of weird, but watch carefully why. Because aren't these my values that are 30, the 3 values below? So what's the value above that? Because doesn't it say percentile says percent below that? Not of it. So my 30th percentile is actually the 80 because the 30% is below that. Some people would say 72 because they think, oh, that's the third. No, no, it's not the third. I want the number above that. So the 3 below are what we're looking for. So when I say 30th percentile, I find 30% of the how many terms we have, and then I count over and say that is my 30th percentile. So what is an outlier? It is a value that is substantially different from the rest. So it is a value substantially different than the rest. Different than the rest. So for this particular situation, are any of these values substantially different? Not really. So does this really have any outliers? Not really. Now, if all of a sudden you had a 50-degree temperature, that's out there. I would call that outlier substantially different. If I had a 130-degree temperature, we're not on planet Earth. Or we're not normal temperature. So outliers are ones that are substantially kind of a way different than the rest. So for this particular one, for this particular data, I do not have any. So I have none for this one. So range. Range is the difference of your data. It's the difference between the largest and smallest value of the data. So if I want the range, I want the difference between the smallest and largest value. Let's start with the largest. From the difference between the largest and smallest value. So for this particular problem, can you tell my largest value is 95, my smallest value is 70, so my range would be 25 degrees for this problem. I go from a high of 95 to a low of 75, so the range of temperatures in those 10 days went from a 25 degree span. If I want to find my interquartile range, I look at the quartiles and find the range of the quartiles. Now to get the range of the quartiles, you have to understand quartile 2 is in the middle. So we basically want the range from quartile 3 to quartile 2. So I want the difference. I want the difference between quartile 3, which is the biggest, and quartile 1. The difference between, I should have put the word between there. Is that better? Difference between quartile 3 and quartile 1. Quartile 2 is always in the middle. So the difference between the quartiles, and for this particular problem, quartile 3, so my quartile 3 is, what is it? It's 90. It's Q3 90. And my quartile 1 is what? 72. So what do you get when you subtract the two? Is that 18 degrees? Now, should your interquartile range always be smaller than your regular range? Shouldn't this always be smaller? Because it's the internal range of it. The quartiles, the internal part of the problem. Standard deviation is an important measure of variation. What the standard deviation is saying is how much the data varies from the mean. So how much a piece of value varies from the mean. Okay? So, let me write that out. I got to write small on this one because to fit it, it's how much a value varies from the mean. A value varies from the mean. Now there is a calculation to calculate that. Okay, so you want your standard deviation is how far the values are spread out, basically. How spread out are they? It's kind of what it's saying. The formula for this is kind of weird. So watch carefully. It's kind of a weird formula. It's going to kind of blow your mind. What you do to find the standard deviation is you take the summation, and that's this little sign, sigma, of each term, each individual term, minus the mean, and square it. And then I divide by the number of values I have. So I take the sum of each term, and first of all, I take each term and subtract the mean, square it, and I sum it up. Then I divide that by the number of values and square root it. And that will give you the standard deviation. So let's do it with our data. I'm not going to do the whole thing, but you'll see the basic idea here in a second. What I'm going to do this is I need to do a square root, And what I'm going to do is take each term. So the first term in our data was 70 when it was in order. I'm going to subtract the mean, which is 82.7, and I'm going to square root it, plus, I'm summing all of them, all the way from 70, and then I'm going to go all the way with 72, then 80, all the way to the last term, which is 95 minus the average, and square it. So I'm going from the smallest number, subtracting the mean, squaring it, all the way to the last number, subtract the mean, square it, and divide by the number of values. So my number of values is 10. Can you see how that would be very long? And a calculator is very essential for this. Now the answer to my particular problem, because that would take you a while, is, just so you have it, is 8.62. That would be my standard deviation. How much it varies, a value varies from the mean. Now the next part is z-score, and z-score represents how many, or the number of standard deviations a value is from the mean. So how many standard deviations are you from the mean? So let's do that out. Z-score is the number of standard deviations. I'm going to put SD for standard deviations. A value is from the average, or the mean. So can you tell for z-score you first need to find standard deviation to some extent? Because it wants to know how many standard deviations you are from the mean. And the formula for this one, to do this, you're going to take the value you're looking for, subtract the mean, and divide by the standard deviation. That will give you the z-score. That will give you the number of standard deviations a particular value is from the mean. So let's use the number 72 degrees. 72 degrees, is that quite a ways from the mean? Yeah. My question is, how many standard deviations is that from the mean? Well, can you tell it's at least one? Because if you look at this, 8.62 is one standard deviation. So isn't that farther than 82.7? So I know it's going to be over one standard deviation. Let's use the math calculation of this formula. Let's use the formula. My number is 72 minus the mean, which is 82.7, divided by my standard deviation, which is 8.62. If we used a calculator for that, again, another calculator cruncher, and did that, my answer would be negative 1.24. That would be my z-score of 72%. Now what that means is I'm 1 1/4 standard deviations below my average. Do you see how you first need to find standard deviation before you find a z-score? And these two interrelate. You can only go so many standard deviations before you're outside the data. If I had 2 standard deviations or 3 standard deviations, I might be outside the data by then, which should make a little bit of sense. Next section is working with samples. And what is a sample? A sample is basically some values of the data, a specific piece of the data. Not all of them, but some of them. So I would call a sample is some values of the data. Some values of the data. Now, let's just choose, for this particular problem, I'm going to choose the last 4 temperatures. That's my sample. Is that okay? So for this problem, I'm going to do the last 4 days. So what's the temperature of my last 4 days? It's 90. 95, 90, and 72. That is my sample. Now, is my problem in itself a sample? Yeah, I only have 10 days. So mine really is a sample of maybe it's spring, but that could be a sample of the whole year, which is a sample of it. I mean, you could keep going. But I'm taking a sample of my data to start with. Now, go over here. What's a random sample? Is this a random sample? Well, no, because the definition of random is everything that's likely to occur. Let me write down the definition of what a random sample is. All values are equally likely to occur. So, if all values are equally likely to occur, is my sample random? No, didn't I specifically choose the last four? What would four random values look like? Well, I just randomly, that one, and point to one, and then point to another one, and point to just four random, or picked them out of a hat. That's random. So this is not random, because all the values are not likely equal. I chose the last four. The other ones had no chance, because I chose the last four. So for this particular problem, is it random? It's not random. Okay, this particular problem, it's not random. Now, the next piece is, I want to talk about this, but I'm going to go down here, sample size. What is my sample size? Can you tell it? Is it right there? My particular sample size is 4 days. But what is a sample size? Well, or how does sample size affect the reliability? Well, do you think a bigger sample size or smaller sample size is more accurate? Could you say that you want to get the biggest sample size possible to be the most accurate? And doesn't a smaller standard deviation tend to mean your values are more accurate? So, for this particular problem, we are doing 4 days. But sample size, basically, a larger sample size has a smaller standard deviation. Let's make sure you write that down. A larger sample size should have a smaller standard deviation. And it's usually better to get as big a sample size as possible. Now, for this particular problem, do I have a good, what's my sample size? I only have 4 days. That's terrible. You're going to see as we do these two things right here, you're going to notice a sample size of 4 days is stupid. It's way too small. You can't go that small and get accurate information. And you'll learn that as we talk about the next couple questions. All right, let's now talk about sample proportion. Sample proportion is the percent of time a value will occur. So let's write it as the percent of times a value will occur in your sample. Okay, in your sample. All right, so the percent of time a value will occur. Well, let's choose in this sample 90 degrees. So for the sample, the percent of times it occurs, well, there's 4 numbers in the sample. And how many of them are 90? Look right here, 2. So that would be 2 out of that. So we have a 50% sample proportion. That's kind of bad, but we'll talk about that. Because we have such a small sample size, a 50% of the time is a little too big for something to occur in my mind, because it's twice out of the 4. But the main reason is we only have 4 values to choose from. Now, that's your sample proportion for a value in a sample. Now the margin of error relates to the sample proportion. The margin of error is the likelihood, or the likely range. It's the likely range for the true proportion, the true population proportion, for the true population proportion. Now the true population proportion, this is a sample proportion, 50%. What would be the true population proportion? And it's the likely range for the true population proportion. So it gives you, margin of error is kind of how accurate your sample proportion is. Within what range is it going to occur? So what that means, again, is, so the margin of error, the formula for margin of error is simply going to be, it's plus or minus 1 over the square root of n. N stands for the number of terms. N stands for the number of terms. So the number of data points or terms. Okay, so it's 1 divided by the square root of the number of terms. So for this particular problem, well, let's look at it. In this particular problem, we have how many terms? We have, I messed that up. How many terms do we have? We have 4 terms. So we would put 4 right here. So what we have is plus or minus 1 over the square root of 4 terms, which the square root of 4 is what? You should recognize the square root of 4 is 2. So it's plus or minus the square root 1/2, which is plus or minus 50%. Now, that's bad, and here's why. Okay, I gotta kind of keep squeezing this in, not running out of room. If 50% is your sample proportion, your margin of error means we're going to go up 50% and down 50% from there. Okay, so think about that. So 50% of the values is this, and if we go up 50 cents and down 50%, that means that that's 100%. Let me show you a little picture of what I'm saying. So if we have a little bar graph here, not a bar graph, a little line graph. If this is 50%, that's my, that is my percent sample proportion. Oh, by the way, that's 50%, not 50 degrees. So 50% there is in the middle. And if we're going to add and subtract 50% to that, that means if I add 50% this way, won't you be at 100%? And if I subtract 50% this way, won't you be at 0%? So your margin of error is kind of like 100%. Okay, that is the likely range. See, the likely range of the true proportion. So the true proportion, it fits the whole thing. That doesn't make any sense. So it's a bad example because there's such a bad small sample size. Our sample size is way too small. So this would work better. But technically what you do with this margin of error is how far left or right from your sample proportion is. And that will give you the range from high to low of your true population proportion, actual of the full population. Kind of weird. Hopefully you'll get used to that with a little bit of practice.